In our last lecture, we learned about the topic of energy, how we could put energy into a system, how we could take energy out of a system. We did this by doing work, the application of force over a distance. And we found that once we put energy into a system, it could take a couple of different forms. It could turn into energy of motion, something called kinetic energy, or it could turn into energy of position, called potential energy. And even in the case of potential energy, it could take a couple of different forms. Maybe we store energy in the form of lifting an object, or maybe we store energy in the form of compressing or elongating a spring. Now these aren't exclusive either. You could store energy in a variety of different ways, but there is only one kind of energy of motion for kinetic energy. In this video lecture, I'd like to look at a lot of different examples of how we apply the topic of energy to problems. A lot of the stuff that we're going to see in these applications are some of the relatively straightforward and easy ones that could be done in other ways. Maybe we could do these exact same problems with Newton's laws and kinematics if we so chose to, but we see that it's more elegant, more quick, and probably less likelihood of getting the problem wrong by using energetic techniques. And in this technique, what we're working with is something called conservation of energy, and more specifically for us, conservation of mechanical energy. It turns out energy can take a lot of different forms, as we said last time. Maybe this is using the energy mechanism in a cell, like mitochondria. Maybe we're looking at action potentials for a chemical reaction or something along those lines, but that's not what we're dealing with here. Right now we're looking at conservation of mechanical energy, those kinds of forms of energies that we've talked about so far. How can we basically have that energy slosh around into different kinds of pots? So here, let's first look at one note here first. So if we put energy into a system, it is there until we do some kind of work to take the energy out of the system. But once it's in the system, it can take any of a variety of forms. 10 joules of kinetic energy could be converted completely into 10 joules of potential energy, or vice versa. Maybe there's an incomplete conversion of potential energy to kinetic energy, or vice versa. But once the energy is in the system, it has to take one of a couple of different forms. And the forms that we're most interested in are these energies shown right here. The first one is really not necessarily energy in the system, but this is how we put energy into the system or take energy out of the system. But the other forms, kinetic, spring potential energy, gravitational potential energy, are relatively straightforward. And using just these concepts of different types of energy, there's lots of problems that we can do and compare answers to ways of doing problems in slightly different ways. And so while there are some other notes in the Canvas notes, and there's a number of different examples, I'd like to walk through a couple of these examples in more real time here. And one of the first examples that we want to look at is the case of a frictionless ramp. And to look at this frictionless ramp, we say, well, here we've got our ramp. We've got a block of mass m on the ramp. There is a normal force. There is a weight, mg. And we're going to say that the length of the ramp is some length L. This angle with respect to the horizontal is an angle theta. So this is a regular setup. Artistically not very great, but I think it gives an impression of some things that are going on. So one thing we want to do is find the component of the force that goes down the plane, like so. And so using Newton's second law, I'm going to try to do this old approach first. We would say that going down the ramp, if we have acceleration down the ramp, which we do, that mg sine theta is the component of force down the ramp, that it has to be equal to mass times acceleration. mass of the free body diagram times the acceleration down the ramp. M cancels with M, and we see that the acceleration of this block is g sine theta. From here, we can use kinematics. Namely kinematic equation number 4, that says that the final velocity squared is equal to the initial velocity squared plus 2a x final minus x initial. And so using this approach, what we're really trying to find is speed of the block at the bottom of the ramp. Like so. Now looking at this, if it starts from rest, we have found the acceleration. This distance is L. I see that v final squared is equal to 2 times g sine theta times L, or that this final speed is the square root of 2gl sine theta. So we can certainly solve this problem to find the speed of this block at the bottom of this frictionless inclined plane. What if we wanted to use a different approach? What if we wanted to use energetics instead? Now what we would say is at the top of the ramp it's sitting at rest, but it does have energy of position, mgh. And at the bottom of the ramp, we're going to completely convert this energy of position into energy of motion, 1/2 mv squared. Okay, well, how do we find the height when it starts? Well, we use trigonometry for that. The height is L sine theta. And that's going to be equal to 1/2 mv squared. The m's cancel on both sides, just like it did before. V squared is equal to 2gl sine theta, and the velocity is the square root of 2gl sine theta. That should look familiar. Because it's the exact same thing algebraically that we found here. This shouldn't be a surprise. I mean, physics builds on itself, and we learn different tools about how to do things, but we shouldn't expect different answers depending upon how we do the problem. Physics is going to do what physics is going to do. So this is a really slick way, if what we're concerned with is finding the final velocity of this block, to find it. I just had to know what potential energies look like. I had to know what kinetic energies look like, and I had to know that there was a complete conversion of one into the other. That's really pretty slick. Now, for this frictionless ramp problem, is this the only thing that we could ask? So there are a couple of things that we could ask. Speed of block at bottom. We could ask acceleration of block. We could ask time to get to bottom. And if I thought about it, there's probably some other things that I could ask as well. Now, using our old approach, one thing we had to do was find the acceleration. But I don't know anything about acceleration over here with energetics. Energetics doesn't lend itself to questions of acceleration, so I would not want to do energetics. For this question, I want to use my old techniques. Similarly, over here with energetics, I don't see anything about time. I don't even know how I would incorporate time, except for to find the initial and final velocity, plug that into a kinematic equation to find time. But if I'm concerned about times, and I have to use kinematic equations anyway, I don't really want to use energetics for this either. The only real thing where the energetics was a huge advantage was this thing right here, the speed of the block at the bottom. And so while there are some things that could be asked that are easier to do with energetics, there are other things that you could be asked that are easier to do with Newton's laws and kinematics. So you have to know kinematics and you have to know Newton's laws, but if you know kinematics, Newton's laws, and energetics, those are going to give you a lot of the things that you need to do to approach problems, depending upon what things are going to be asked of you. So this is a good place to start by seeing how energetics and traditional techniques of force and kinematics compare with each other. And you get the same answers doing things either way. Well, what's another problem we could do? We could look at the case of a pendulum. And maybe with this pendulum, we've got this ball of mass m that's at the end of a string of length L. And it follows along the path of a circle here. It's still length L. This is still mass m. And this is, some radius of curvature that it has. And maybe we know the speed of the block here is given as m. And I would like to know what the speed is when the mass is at this location. And maybe another bit of information that we need here is that this is some angle theta. Well, one thing that I know is if we were to set this as our zero of potential energy, as the block is moving, it is going up some height h. So when it's down here and we are at the zero of potential energy, we don't have any potential energy. We only have kinetic energy. But here at this location, we have some kinetic energy and we have some potential energy, mgh. Now, we weren't really given h in the problem. We can figure out what h is by using the given values of L and theta. And so we see from trigonometry here that this side is L cosine theta. And this side is L. So this must be L minus L cosine theta. And that's what h is. L minus L cosine theta. That's what h is. So now obviously we can factor out that L. And so we are converting our initial kinetic energy into some kinetic energy and some potential energy. Okay, well, if I wanted to know what the speed is at that location, I want to find what Vf is. So 1/2 m Vf squared is equal to 1/2 m V squared minus mgl 1 minus cosine theta. I can multiply everything by 2, divide everything by m. V final squared is equal to the initial speed, the speed at the bottom squared, minus 2gl, 1 minus cosine theta, or that final speed is the initial speed squared minus 2gl, 1 minus cosine squared cosine theta under a square root. this is what the speed is at that location. And it is smaller than it was when it started. As you can see here, for example, let's set theta equal to 0. If theta is equal to 0, we're back at the bottom again. Cosine of 0 is equal to 1. 1 minus 1 is equal to 0. The speed at the bottom is the speed at the bottom. Now, what if we were to let theta go to 90 degrees? So this thing rotates until it's horizontal. The string is horizontal. Cosine of 90 degrees is equal to 0. 2gl 1 minus 0, v squared minus 2gl. This is a smaller speed than it was before. Okay. Well, what if we were to let theta go to 180 degrees? So this mass is going around the circle until it gets to the top of its motion. Now all of a sudden theta of 180 degrees, cosine of 180 degrees is minus 1. 1 minus negative 1 is 2. V squared minus 4gl. This is an even smaller speed. So as this mass goes up and up and up and goes around the circle, its speed is changing. It's going down because we're raising the potential energy, and that energy had to come from somewhere. It comes from taking it out of the kinetic energy that we had at the beginning. Now I see equations like this, and I see V finals are related to V squared minus some other sort of thing that has 2gLs and things in it. And I think to myself, this is kinematics, right? Why couldn't I have done kinematics for this? Sorry. And the reason why is the acceleration is not constant. As this goes around, the only thing that can slow this mass as far as putting work into the system is gravity, right? The force that is applied putting work into the system is gravity. But depending upon how this thing is moving, how this thing is displaced, F and that path along the path of this circle are not always the same. That means acceleration is not constant. So the acceleration of this thing is not constant. It's not freely falling. It's got strings attached to it. All sorts of stuff is going on all the time in terms of this acceleration. And because the acceleration is not constant, we can't do kinematic equations. You might get expressions that look like kinematic equations, but you can't motivate it through kinematic equations because the acceleration is not constant. So if you're wanting to use kinematics, you can do integrals, and you can integrate components of force over certain sorts of angles, and things might end up looking familiar. But that would be because of a mathematical oddity. As far as the motivation, acceleration is not constant. You can't use kinematic equations for this. Energy is the way to do it, unless you are pretty sophisticated in knowing how to do these integrations. Okay? Something to keep in mind. In this problem, acceleration was not constant. Now we're going to come back to a problem like this problem a little bit later with the loop-de-loop. And we saw the loop-de-loop problem last lecture. I mean, for last week when we were talking about forces and things were going around loop-de-loops. We saw a little bit of that. I didn't dwell on it during lectures because it comes in a more complete form in this lecture. So we're going to do a little bit more with it here, and it's related to some things that we saw here with the pendulum, touching on a couple of those topics of circular motion. Okay, well, what's another thing that we could potentially look at? We could look at the case of projectile motion. We've already done projectile motion. Right? And maybe we have some cliff, and we're firing some projectile from the top of the cliff, and the cliff starts at some height h. We see that the projectile hits down here, some distance r away from the cliff. It was fired at some speed v, at an angle theta with respect to the horizontal. This is a relatively straightforward problem. Now, as we're looking at this, are we ever going to do a complete conversion of potential energy to kinetic energy? Well, it turns out we start the problem with some kinetic energy, right? It is being fired from the top of the cliff. And if this is our zero for potential energy, the way we start the problem is with mgh of potential energy and 1/2 mv squared of kinetic energy. That's how fast that thing is moving. Okay, well, what if we wanted to look at a case of maybe finding, okay, well, where is the maximum height? We can actually use conservation of energy to find maximum height. And as one aside here, we're still at position 1. One clever way of writing this 1/2 mv squared would be to write it as 1/2 m v squared cosine squared theta plus 1/2 m v squared sine squared theta. Cosine squared plus sine squared is equal to 1. This is the same thing. But what we find here is if we were to analyze the motion of this projectile going along this trajectory, when it gets to its maximum height, we haven't converted all of the kinetic energy into potential energy because there's a certain amount of kinetic energy we can't get rid of. Notice with a projectile motion problem like this, the horizontal component of velocity can't change. There's no acceleration in the horizontal component of velocity. So from this, we can never get rid of this. So this is energy that will always be in this problem. But the thing is, I can convert energy that we have in other forms into height. So max height plus this energy we can't get rid of. Sorry, mv squared cosine squared theta. So apparently, mgh, the height of the cliff, plus 1/2 m v squared sine squared theta has to be equal to mg h max, the maximum height. Because this energy and this energy is the same on both sides. So now I can divide everything by m, multiply everything by 2, actually divide everything by g would probably be better, and I see that h max is equal to h plus v squared sine squared theta over 2g. And if you remember from kinematics when we were doing projectile motion, this is how high the projectile went if you fired from the ground. So if I fired from the ground, it goes up v squared sine squared theta over 2g to get to its maximum height. Another way we could have looked at this, because what's happening in this horizontal component doesn't change, we could have just looked at the vertical direction. And we could have said that mgh plus this component of velocity squared, this is this vertical component of velocity, is equal to this. But we're doing the same thing. These two equations are really the same equation. So there's nothing different about these approaches. So we could have done this all vertically. We could have looked at components and figuring what kinds of motion contribute to different kinds of motion. But to get the maximum height, that's relatively straightforward to do. And we get answers that are consistent with what we have seen in the past. Maybe we wanted to find out how fast is it moving when it hits the ground. So I know at its initial position, it has mgh of potential energy. It has 1/2 mv squared of kinetic energy. But when it hits the ground, it only has kinetic energy. That's it. All the potential energy has been turned into kinetic energy at this point. So if I wanted to find this final velocity, I can multiply both sides by 2, divide both sides by m. And notice I didn't have to pay any attention to the angle. I didn't have to break up components or anything like that. I was converting potential energy into kinetic energy. This potential energy is being converted into kinetic energy. We still have the kinetic energy that we started with, but now all we have is kinetic energy as we're putting everything together. And this is the exact same answer you would have gotten for final speed using kinematics. So looking at a question like this, man, energetics is great. Now, what if we were asked, what is this range? Energetic doesn't give me any good way to get to that. I have to know a little bit of kinematics to do that, because sure, I can find things about velocity and components of velocity, but I don't really have time. I don't have range worked into this. So while energetics is great for finding certain things, energetics is not the correct approach for everything. This won't give me time in the air. This won't give me range. I have to do kinematics to do things like that. So just be aware that there are some aspects of projectile motion problems that are easier if you know energetics, but there are some aspects of projectile motion problems that you still have to go back to the old tried and true kinematics, which is useful to know. What if we had a different type of problem? What if we had the Atwood machine? What is the Atwood machine? So I've got this big pulley here. Got some mass m1, got some mass m2. We're going to start with m1 at distance h above the ground, but m2 is touching the ground. Now this is very similar to the problem that's shown here. So let's try to do this problem. So in this problem we have a system of 2 paint buckets connected by a lightweight rope. It's released from rest with the 12 kilogram bucket, what I'm calling M2, or what I'm calling M1, a distance 2 meters above the floor. Use the principles of conservation of energy to find the speed with which this bucket strikes the floor. I don't have to worry about friction yet. I don't have to worry about the mass of the pulley. These are actually problems that will come up later. So it's a very similar problem to what I've sketched out here. So maybe I've turned the masses around, but so what? The way we start the problem is one of these paint buckets, what I've called M1, has potential energy. M1 GH. My M1's hard to read, so let me write it a little bit better. M1 GH. I would like to let the system evolve, and we know that if M1 is bigger than M2, these are going to accelerate. That's Newton's second law. This is the Atwood machine problem just like we did last week. So if M1 is bigger than M2, both of these masses are going to accelerate. M1 is going to accelerate down, M2 is going to accelerate up, which means that both of these are moving at some certain velocity all the time. So as M2 goes up to a height h and M1 goes down to a height h, they will get both of them to the same velocity, v, meaning that each of them will have respective kinetic energies, 1/2 m1 v squared and 1/2 m2 v squared. But what else is true? M1 has fallen down, but M2 has risen up. We still have some potential energy, M2, GH. So we start with potential energy associated with mass 1. Nothing is moving. That's all the energy we have in the problem. As the system evolves, some of this potential energy is converted to kinetic energy for mass 1. Some of this energy is converted to kinetic energy for mass 2. And the leftover energy is energy of position for mass 2. So if I wanted to find out how fast these things are moving when M1 hits the ground, that's the problem we have here, and this is the problem we're asked for. Use the principle of conservation of energy to find the speed with which the bucket strikes the floor. That's what I'm asked. So I need to find v, or v squared first, and then find v. So I see that m1 minus m2 gh is equal to 1/2 m1 plus m2 v squared. Here I'm just doing a little bit of algebra. I'm pulling this term over to the other side, grouping these terms together. They both have the same speed. They both have the same 1/2. From here, v squared is equal to 2 m1 minus m2 gh over m1 plus m2, so that the final velocity is given here. And in this problem we're told what m1 and m2 and g and h are. So the h for this problem was 2 meters. M1 was 12 kilograms. M2 was 4 kilograms. This is all the stuff that we need. So we can go to our calculator, and I've got a 2 times 12 minus 4, which is 8, times 9.8 times h is 2, divide by 12 plus 4 is 16, and take the square root. So 4.43 meters per second. Now again, in this problem, what we were asked for was some final speed. Final speeds are great with energy. Anything with speed and how speed is related to position is great with energy. This is not good for finding time. This is not good for finding acceleration unless we wanted to use information here with our kinematic equations. And that's totally fine. There's nothing wrong with that. But just be aware that what energy is built for is looking at relationships of how position and velocity are related to each other. It's not really doing it through acceleration. It's not really doing it through position, except for in how it's related to velocity. So once again, we've done this kind of problem. We could have done this problem with either of the last two units, particularly once we knew force, of course. We could have done this, and we would have found exactly the same answer, the same algebraic answer, by using Newton's laws and kinematics. So finally, before we get into a discussion of friction, we can look at a discussion of some loop-de-loop. Maybe we've got radius r, and we've got some ball that's rolling along, and we would like to give it enough velocity so that it can go around the loop-de-loop, but at the top of the motion, the track doesn't have to push on it. How fast does the ball need to move at the bottom so that it gets around the loop but just barely. Just barely around. So it doesn't have to push down at the top. It just gets around but keeps moving. So once again, this is a configuration where we are not completely converting kinetic energy into potential energy. If we were doing a complete conversion of kinetic energy to potential energy, the ball would have to stop at the top. And the only way that's going to work is if the track is pulling up on it. Right? If it's going to stop at the top, it has to be sitting with the track holding it up. That's the only way it can do that. But this ball is rolling on the track, right? It's going around to the top, and if the track is not able to hold it up, it's going to fall. It has to have some speed so that it makes it around the loop. Now this is related to stuff that we were talking about last week with motion of this ball going around the track. And last week we said, well, what if we knew the speed as it was going around different parts of the track? And if we know the speed, we can figure out what the centripetal force is. We could relate that to centripetal accelerations. And yeah, that's kind of an interesting problem. But what we didn't know last week is why or how does the velocity of the ball change as it's navigating around the circle. But we already saw with the pendulum that as this ball goes around the circle, it's partially converting kinetic energy into potential energy. And if we want the ball to make it all the way around the circle, it has to be moving at the top. It can't be a complete conversion. It can only be a partial conversion. So the first thing we might want to find is how fast can the ball go at the top so that it gets just barely around the loop. And for here, we have our free body diagram of the ball. And at the top, the track can push down on it. And in theory it could. But the ball also has some weight, mg. And we see that we need some centripetal acceleration, right? So from this free body diagram, we see that N plus mg is mv squared over r. That's the centripetal acceleration that's needed. And we would like to look at the condition where the track isn't touching it at the top. So it's just barely making around the circle. So if I wanted to figure out how fast it was going, I can divide both sides by m, and I see that v is the square root of gr. The ball has to be moving at the square root of gr at the top, or it doesn't navigate the circle. Any speed lower than this, and the ball could trail off and leave the circle. Any speed faster than this, and the track has to push it down. So it's not really barely making it, because the track still has to hold it. So this is the condition at the top of the circle for the ball to just barely make it around. So if I'm looking for a condition, how fast does the ball need to be moving down here so that it just barely makes it around the circle? At the bottom, we only have kinetic energy. I'll call this V bottom squared. But at the top, we have kinetic energy and we have potential energy. And what is the height? R plus R, 2R. So this is the potential energy at the top. This is the kinetic energy at the top to just barely make it around. And initially, all of that energy was kinetic energy at the bottom. So if I want to find out the speed at the bottom, I can multiply everything by 2, divide everything by m. Velocity at the bottom squared is equal to velocity at the top squared plus 2mgr. So what is the speed at the top? It has to be going the square root of gr. The square root of gr squared is gr. Oh, we don't have m anymore. This is gone. So this is gr, and, oh, we have to multiply this by 2. 2, so this turns into a 4 here, plus 4gr is equal to 5gr. And here, I want to make sure I'm doing my math right here. Okay. Multiply by 2, 2, 2. So this 2 turns into a 4. It's still 2 here. Divide by m. So this is 4gr, 5gr. Okay, good. And this is the v at the bottom. So if you give it this amount of speed at the bottom, it can make it all the way around the circle and have enough kinetic energy at the top to navigate and get all the way around. So this actually has lots of information. What if we wanted to find out how fast the ball was going here? Well, this is just the projectile energy problem. What if we wanted it to stop at some certain angle? We could do that. If we wanted to stop at a certain angle, or we could find out what its speed is at any angle, right? If we wanted to, this is h. So here we have this speed at the bottom, and I'm just going to call it v bottom. Okay. But if we wanted to find out what its speed is at any angle, At any angle, we're going to have some different kinetic energy, but we're also going to have mgh, or in this case, where h is r minus r cosine theta. This is going to be the height that it is for any given amount of angle. So if I wanted to find that speed, I would do it the same way that I did for the pendulum problem. Or if I wanted it to go to some particular final angle, how fast does it need to be moving at the bottom so that it stops at that certain angle? Well, we could do that. What's the speed at any angle? Given some speed, how does it get to a final angle? There's lots of things that we could do. And so you could go and look at the already pre-worked examples that I've done in the Canvas shell, but this just gives an idea of the flavor for how to do loop-to-loop problems like this. There's a whole class of them. Maybe we wanted to have a ball, it goes around a loop, and then it goes on some ramp. And if we know it has just enough speed to make it around this particular loop, well, how far does it go from the edge of the ramp? So we're basically using energetics to figure out how fast the ball is going, and then once we know how fast the ball is going, we can navigate a ramp, we can do projectile motion. There's lots of things that we could do from this. So it's kind of an interesting problem, a certain class of problems. Anyway, now that being said, none of these problems that we looked at here had any friction. What if we wanted to look at some problems that had some friction that were associated with it? Well, it turns out that if friction is involved, friction is going to do work in the problem. And as you might suspect, friction is going to take energy out of a problem. Because it is doing applications of force to reduce relative velocities between two different surfaces, it could take a situation where a block had initial kinetic energy and take all of that energy away, so it's just sitting there at the same height that it was before. Where did the energy go? Well, it went into heat. It went into sound. It went into some energy of vibration. It could go into a lot of different things, but none of those forms are mechanical. So frictional forces don't get rid of energy, but it gets rid of energy that was formerly mechanical. So that being said, if we had some situation where at the beginning of a problem, we have kinetic energy, and we have potential energy. But later on, as the problem evolves, maybe the block is still moving, and maybe there is some potential energy of some kind, but we have also energy turned into heat. Etc. And that's what friction is doing. So we're going to get expressions like 1/2 v initial squared plus mgy initial is equal to 1/2 mv final squared plus mgy final plus some sort of a work due to friction-y kind of term. Frictional force over some distance, kind of a term. So if you're doing accounting, maybe this is 10 joules, maybe this is 0 joules, and it could be converted at some time later into 2 joules, 3 joules. Oh, well, this is 10 joules. This is 5 joules. we might have taken 5 joules and sapped it out of the problem. And if we were to wait long enough, maybe we would find out that all of our energy got burned away. Maybe the friction is just so that it could slide up the ramp, but then it stops at some position on the ramp. So yeah, it could be an incomplete conversion, but it certainly totally could be a complete conversion. And so we could look at problems like this as well. Now, one of the problems that I have in the book was a condition, it was the problem shown here. And I know this lecture is getting slightly long, and so I'm going to leave that to you just watching it off of the Canvas shell if you choose. But I was going to look at this problem here, where I have we haven't done anything with springs, have we? We have not done anything with springs. So I am going to do this problem. I was going to look at a case of just a block sliding on a table and all of our energy is burned away. But let's do this problem instead. So in this problem we have a block. It has a certain mass. It's attached to a spring of some certain force constant as shown. The block is pulled to a position 5 centimeters to the right of equilibrium and released. And we're asked to find the speed of the block as it passes through equilibrium. First, if the horizontal surface is frictionless, and later if there is a coefficient of friction between the block and the surface. And so this actually looks at springs in a slightly different way. And maybe this is more useful. Okay. So what do we have in part A? In part A, we start the problem, and the potential energy, at least gravitational potential energy, never changes. Our spring potential energy could change, and what we start the problem with is no energy of motion, but spring potential energy. 1/2 k, let's call it d squared. It looks horrible. So 1/2 k d squared. Now, as it goes through equilibrium, what we mean by equilibrium is there's no energy stored in the spring anymore. So as it goes through equilibrium, we're not getting gravitational potential energy out of it. We don't have friction in part A. It can only take the form of kinetic energy. So if we want to find out the speed of this object as it goes through equilibrium, this is what we're calculating. V squared is going to be k over m d squared, or V is the square root of k over m d squared. And in this problem we know d, we know k, and we know m. K is 500, m is 2, so this is 250 times 5 centimeters squared under a square root. Let me just put this here so I don't forget. And mass is equal to 2 kilograms, and D is equal to 5 centimeters. So we pull up our calculator, and we have K, which is 500, times 5 centimeters, which is 0.05 meters, squared, divide by mass of 2 kilograms, and I take the square root, 0.791 meters per second. So yeah, we could find that velocity. Excuse me. And what if we wanted to do part B? So now for part B of the problem, we're allowing friction. So we still start the problem with the same energy. And we are certainly going to have some kinetic energy as it goes through equilibrium. But not all of the energy is going to be kinetic. Some of the energy has been lost to friction. And frictional energy loss is associated with a frictional force over a distance. Frictional force is mu times the normal force. Mu mg is the force. The distance is d. That d. As it goes through equilibrium, it's going to come back that same distance that it was pulled out. So this is energy that is no longer mechanical. But we can use this to find out what a final velocity is. So we still have 1/2 mv squared is equal to 1/2 kd squared minus mu mg d. Multiply everything by 2 and divide by m. v squared is k over m d squared minus 2 mu g d, or the velocity now is k over m d squared minus 2 mu g d, all under square root. Now notice here, originally we had the square root of k over md squared. Now we have k over md squared minus some number as the argument of this square root. This has to be a smaller number. This has to be a smaller number. And so we put these numbers into our calculator. And we've got 500 times 0.05 squared, divide by 2. So that's the number we had before. Now we are subtracting 2 times 0.35? Yeah. Times 9.8 times d, which is 0.05 meters. We've got this number now. We take the square root, 0.531. So here in part B, the velocity is smaller. As you might suspect, because we don't have any friction in this problem. Or we do have friction in this problem. Friction is taking some of our energy away. Now I see that the lecture is starting to get a little bit long. There was actually one more example that I was going to look at, which was this problem. But this is already worked out in the Canvas shell. It's another application of a case where if there's a certain kind of thing that we're asking, how fast does it move? Actually, we probably have time to do this. I'm 58 minutes in, so I got to do this really fast. Let's do this problem really fast. So we have these blocks. We can call them M1 and M2. I'm going to call that M1. Here we've got some pulley. We've got M2. Okay. And we would like to look at a case where M2 falls some distance h. And I'm curious how fast everything is going after M2 has fallen this distance. We're told here it's 1.5 meters. So let's look at the problem. What are we starting with? Well, what I'm starting with is M1 is always going to be at the same height. It never changes its potential energy. So I'm going to have some potential energy associated with M2. And this loss of potential energy with M2 is going to be converted into kinetic energy of both of these things. So if I'm starting the problem, I might say that I'm starting with M2 GH worth of kinetic energy. But as I lose that potential energy, it will be used to speed up M1. It will be used to speed up M2. But it turns out that if this is the normal force, and this is m1g, and we have this tension, we have a frictional force here. A frictional force is taking energy out of the problem. And so our normal force is m1g mu m1g times this distance, the distance that this falls, h. So if we want to find out how fast these things are going, we have to solve this equation for velocity. 1/2 m1 plus m2v squared is equal to m2gh minus mu m1 gh, or m2 minus mu m1 gh. So I can actually solve this for v. 2 m2 minus mu m1 gh over m1 plus m2 under square root. This is the velocity. And I can plug this into my calculator. We know a couple of the things here. So in our expression, m1 is equal to 8 kilograms. m2 is 6 kilograms. That's fine. Mu is 0.25. H is 1.5 meters. That's all the stuff I need. So from here I can go to the calculator. And we've got, I'm going to do the parentheses here too. So m2, which is 6, minus 0.25 times 8. So that's the parentheses, times 2 times g times h, divide by 8 plus 6, 8 plus 6 is equal to that. I take the square root of the whole thing, 1.57. meters per second. So yeah, we can find the velocity, and we can have friction involved and everything else. So I know this was a little bit of a long video, and I apologize for that, but I think it does hopefully give you some faith and some confidence working with expressions of conservation of energy. While it's not going to be something that makes every problem easier, it does make a lot of problems easier, and that's the whole point.